Next method is the effectiveness NTU method. And this method is based on a dimensionless parameter called the heat transfer effectiveness epsilon. So epsilon is equal to Q dot divided by Q dot max. That means actual heat transfer rate divided by maximum possible heat transfer rate. So the actual heat transfer rate in a heat exchanger is Q dot is equal to Cc into Tc out minus Tc in is equal to Cs into Ts in minus Ts out. This is for cold fluid and this is for hot fluid. So the maximum temperature difference is del T max is equal to Th in minus Tc in, and the maximum possible heat transfer rate in a heat exchanger is Q dot max is equal to C min del T max is equal to C min Th in minus Tc in. This is equation 32. Once the effectiveness of the heat exchanger is known, the actual heat transfer rate can be determined from this equation. Q dot is equal to epsilon Q dot max is equal to epsilon C min Th in minus Tc in, equation 33. The effectiveness of a heat transfer depends on the geometry of the heat exchanger and the flow arrangement. It can be shown that the effectiveness of double pipe parallel flow heat exchanger is epsilon parallel flow is equal to 1 minus exponential minus UAS divided by C min into 1 plus C min by C max divided by 1 plus C min by C max. This is equation 38. Effectiveness relations of the heat exchangers typically involve a dimensionless group called the number of transfer units NTU. NTU is equal to UAS divided by C min. We can write UAS divided by m dot Cp min. Equation 39. For specified values of U and C min, the value of NTU is a measure of the heat transfer surface area AS. The larger the NTU, the larger the heat exchanger. It is also convenient to define a capacity ratio C, which is C is equal to C min divided by C max. This is equation 40. The effectiveness of a heat exchanger is a function of the number of transfer units NTU and the capacity ratio C. Effectiveness for several heat exchangers. This is table 11.4. Effectiveness relations for heat exchangers. NTU is equal to US divided by C min, and C is equal to C min by C max is equal to m dot Cp min divided by m dot Cp max. So heat exchanger type and effectiveness relation is there. Number 1, double pipe parallel flow. Epsilon is 1 minus exponential minus NTU into 1 plus C divided by 1 plus C. And for counterflow, epsilon is equal to 1 minus exponential minus NTU into 1 by C, 1 minus C divided by 1 minus C into exponential minus NTU into 1 by C, 1 minus C. Number 2, shell and tube. One shell passes 2, 4, 6, 8, something like that. The multiplication of 2 tube passes. This is the equation or effectiveness relation for this. Number 3, cross flow, single pass, both fluids unmixed. C max mixed and C min unmixed. C min mixed and C max unmixed. And the last one, for all heat exchangers with C is equal to 0. The relation is epsilon is equal to 1 minus exponential into minus NTU. From WM Case and AL London Compact Heat Exchangers, 3rd edition, MC Grohill 1984, reprinted by permission of William M. Case. Next topic, effectiveness heat exchangers plots. There are 6 different figures. First one is for parallel flow. Number B, counter flow. Number C, cross flow with both fluids unmixed. Number D, 1 shell passes and 2, 4, 6 tube passes. Number E, 2 shell passes and 4, 8, 12 tube passes. And number F, cross flow with one fluid mixed and the other unmixed. So there are 6 different types of effectiveness heat exchangers plots.